the Gauss theorem has major applications in symmetric cases. So by symmetric cases, what I mean is spherical symmetry, now in spherical symmetry you will have point. If you try point symmetry, you will reach Coulomb's law. Then you have shell, and C you have sphere. So we will find Gauss theorem is exactly Coulomb's law, and it is Coulomb's law is valid only in spherical symmetry. Okay. Now Gauss theorem in gravitation will show that Newton's law of universal gravitation is also valid only in spherical symmetry. For all other cases, we have to use calculus. Now the next symmetry is cylindrical. Now in cylindrical, you can have A infinite wire, you can have B infinite. So everything has to be infinite, cylindrical. Cylindrical shell, and C is solid cylinder. Right, and the next symmetric case would be planar. Now planar symmetry, thin infinite sheet, thick infinite sheet. Right, and then there will be combination of sheets. Now this you can think of as a mind map for this chapter, and in AP ENM there is every time or maybe every second year at least one FRQ on any of these things. I have seen for solid cylinder, I have seen for shell, I have seen for plates, thick, thin. So today's class will give you one FRQ. Okay, let's begin with the Gauss theorem. Now, as I said, the Gaussian surface. Now, what is a Gaussian surface? A surface that is enclosing completely. Okay, so let's take the first case, point charge. Now, point charge Q is there. Now, what we are going to do is we are going to make a Gaussian surface at a radius r. Right? And now we are going to apply the Gauss theorem. So according to Gauss theorem, the total flux is E dot dA integral. Now, as I said, it's an enclosing Gaussian surface, so every time there has to be a circle. Integral, and then there is a circle. This means it is written for the surface, and this surface is entirely covering this charge. Right, now I'm going to take a patch. Okay, just imagine this is like a football. I'm going to make a patch, and suppose this is the center. So this is my radial direction. Is this clear? Right, this is my radial direction. Now, if I define dA, I discussed before, how do I define dA? dA area vector such that dA is actually the area and it's along the radial direction, right? Because normal from this surface will be parallel to radial vector r. Now this is a unit vector. Is this point clear? Quick.
Yes, sir.
Nidhi, okay. Please open your mic and answer and then close your mic. If you don't follow, interrupt me. Now think about electric field. Now this is a point charge, so it will have a spherical symmetry. The field will be radial as well. So field is like this. Right. So I'm going to write the magnitude of field I don't know, but it is some E radial, something that will also be the function of radius. So I would really write it like, and it is radial. Right. Now if I carry out this dot product here, closed integral E r dot r dot r, and then there is dA. Right. So this r dot r will give me 1, as we learned in vectors. When unit vectors in the same direction, they are of magnitude 1. So this will be E radial dA. Right. And according to Gauss theorem, this is Q by epsilon naught, because Q is the charge inside. Now on the right side, I know field will be constant at this radius, so I'm going to write R and take it out, and this will become closed integral dA. Now this closed integral dA means it's the area of this spherical surface. So that is E dot R times 4 pi R square. So you can see clearly Q by 4 pi epsilon naught R square is equal to, right? Now, according to Coulomb's law, we got exactly the same thing. And at that point, I said 1 by 4 pi epsilon naught is a proportionality constant, and Q is the charge. Because of that, there is the field. Right? So from this, we prove that Gauss law is equivalent to Coulomb's law. Is this point clear? Quick. Yes or no? Any doubt, any question?
Yes. No, sir.
Okay. Now, this Gauss theorem that you are learning now is not going to leave you even in your first year of engineering, because you will have electrodynamics. So what you are learning today will be a startup. Just when you go for electromagnetism course at college, in the first year, it will have just a little bit more calculus. There you would be worried about calculating surfaces and worrying about polar vectors and other things. Okay. So you can clearly see this is a nice way with least amount of maths to calculate flux. Its advantage is only for symmetric cases as listed above. And a lot of times you can check if a formula is correct by using Gauss theorem. Okay, so next we will go for shell and the sphere. So what you are doing in this with the electric field In gravitation, you will do with gravitational field. Okay, so this chapter and next chapter are really important if you want to understand even gravitation with more details. Okay, let's take a spherical shell. This time I have a R shell, and this shell has a Q charge on it. Right, so I can do following. I want to find field inside. Okay, so I'm going to make a Gaussian radius R. And my interest is to find E in two cases, R less than big R and R greater than or equal to big R. Okay, so let's take the case one. Let's say this is E1, this is E2. So again, using the same Gauss theorem, Q inside is 0 by epsilon naught is equal to integral E dot dA. Now, if I make a patch on this surface, and if I connect, this is my radial vector, and then again my field, electric field will be E some radial, right? And dA will also be same. dA will be in the same direction. So I can clearly write E some radial times integral dA. Now I know this thing on left side is 0. On right side, it is product of times 4 pi r square. Right, because this gives me area of this spherical Gaussian surface. So definitely is equal to 0. So this is the E1. Okay, so this we found is 0. Now, without this Gauss theorem, it is very hard to convince people that field inside is 0. Okay, so let's move on. Suppose I take another Gaussian surface like this, and this time I have small r like this. Now you can see in this bigger surface, Q inside is Q by epsilon naught is integral dA. Right, and then you can easily write times 4 pi r square. So you can write that is E2. Let's write this is E1. E2R is equal to Q by 4 pi epsilon naught r square. So you see, in this case, you can think that this Q charge is at the center. Is this point clear? But only for R in this range. Is this point clear? So if you make a diagram, very good. If you make a diagram E versus R, then you can see until big R, it is some value. And this is hyperbolic function like this. And before that, it is 0. Right? And it will continue. Is this point clear?
Yes, sir.
Now, if somebody asks, what is the potential? Okay, I'm also going to do potential. What is the potential as a function of R for this shell? See, the field inside is 0. So whatever work done, right, we define potential write as work done per unit charge. Now this charge is the test charge. We bring from infinity to a location R, right? And now you can see if you are for R less than R, then this will be Q by 4 pi epsilon naught R, because you really have to do work from bringing from infinity to this location R, but not inside. For R greater or equal to big R, this will be Q upon 4 pi epsilon naught R. Okay, and I think there has to be a minus sign. Okay, there is another relation, E is equal to minus dV by dr. So if you take the derivative of this, so this is r to the power minus 1, so you will get this. Okay, is this point clear?
Yes, sir.
So you could have written V is equal to integral E dot dr, and there is a minus sign. Okay, very well. So all these points are clear. So if I draw potential corresponding to this, I'm going to draw here itself, potential versus R. So again, this will be hyperbolic for until R, right? So this will be hyperbolic. Suppose I say it is, this would be more aggressive. So this would be little relaxed, but this is hyperbolic. V is also hyperbolic because you see electric field is R square, potential is R. And then it becomes a constant. So after R, this will be constant. Is this point clear? Everyone, is this point clear?
Yes, sir.
Any doubt, any question? No. Okay. Okay, so let's move on. Okay, let's move on. Okay, so next case is sphere. So suppose I have a solid non-conducting sphere of radius big R. Now my interest is to find the electric field for both locations, R less than big R, R greater or equal to R. So what I'm going to do, I'm going to do the same business. I will make a field. I will make a Gaussian surface with small radius R that is enclosing this area. And I want to find field at one of this point on the surface of this Gaussian surface. Now, what I should get is Q inside by epsilon naught. This would be integral closed E dot dA. Now I'm going to do the exactly same business. Make the patch, and patch will have dA that is radial and will have the field that is also radial. So this will give me E some radius function times the integral dA, which everybody knows, right? if there is homogeneous charge density rho, right? If there is a homogeneous charge density, then I can say if big Q was on 4 by 3 pi r cube, then the Q inside will correspond to 4 by 3 pi small r cube, right? So then I take ratio of them. I have to multiply with rho and rho. Then these will become equal, right? And I take ratios of them. So I can write this is equal to Q in. I have to find Q in will be Q total R cube by R cube, right? And then I just need to solve this. This would give me E radial is equal to 1 by epsilon naught 4 pi, and this will be small r square. So it will become QR by R cube, right? Because if this was R cube, here I would have 1 R square because of 4 pi epsilon naught, 4 pi R square, right? So you can see field is Q by 4 pi epsilon naught R cube into R, right? If I go beyond this, if I make R for the big radius, then my field will become simply Q by 4 pi epsilon naught R square, right? Before it was Q by 4 pi epsilon naught R cube into R, right? Now if I make a graph, I'm going to make two graphs. I'm going to make for potential R and R. So this is my field, right? And this is my potential V. Now until the radius R, the field rises uniformly, linear function, and then there is a hyperbolic decay. In chapter gravitation, this is what you will find for gravitational field below the surface of Earth, above the surface of Earth. Okay, so there just the charge will change with mass, and mass cannot be negative, and so forth, other things. If you take the magnitude of potential, how would it be? Okay, so beyond R, it has to be 1 by R, right? Because if we go for R larger than small r, you would have the 1 by R dependence. Before that, what will be the, so you can think minus E dot dr integral is VR. So E is linear, so you will see minus Q. We are not interested in sign, but you can see this will be R square by 2 and 4 pi epsilon naught R cube, right? So at r equal to 0, it will be 0. So it will be some parabolic function, right? So this will be R square dependence in this region, 1 by R in this. 1 by R square for the field and R for the field. Is this point clear? Please take a snapshot. Any question, any doubt? Quick. Any question, any doubt? Are you people there? Okay.
Yes, sir. I
Nav
think
okay, Navya, Soham. Okay, people are like,
Yes, sir.
you're there. Okay, very well. Sorry. Okay, let's move on. So this is a case for the spherical symmetry. Now, next case we have to do for cylindrical symmetry. But before moving further, in AP electromagnetism, sometimes they don't use constant rho model. They could give you rho is equal to rho naught 1 minus r square by r. Suppose this is the charge density. Okay, then how would you do? Can you redo this with this in mind? Could you give a try? Okay, I give you few minutes to help me solve this. This thing is in textbook, everybody has it. Now please help me with this. So Navya, Pranav,
Yes, sir.
how would you solve this problem? I want to know electric field as a function of R. Any suggestion?
Sir, I think you have to replace rho with the new formula for rho that we have right now.
Exactly. And then we have to use calculus to find charge inside. Because you know, before we did like algebra, because we know the density is right, or the charge is density times the volume. Now it is a function of R. So you can see how is the density changing with respect to R. When it is big R, the density is 0. And when it is 0, it is rho naught. It starts with rho naught and it goes, how would it go like? See, 1 by R square will be like this. And now if you subtract from 1, the density will be like this, right? So at any R, I know the density is rho as a function of R. So what I'm going to do, I'm still going to take the Gaussian surface of small radius R. And then what I'm going to do inside this, I'm just going to have this R. Now, what I'm going to do, I'm going to define a radius A. Okay. And then I will take a thickness dA. Right? My interest is to get charge inside this small r. Now my density rho is rho naught 1 minus a square by r square. Let's take like this, right? And so how much is the charge in this shell? So dq in this shell is 4 pi a square. This is the surface area of this shell of radius a, and then it has a thickness dA. This became the volume, and then I have to multiply with this rho. So I will write rho naught 4 pi, right, a square 1 minus a square by r square into dA. Now if I want to know the charge inside, it will be from a equal to 0 to small r, right? So I can write 4 pi rho naught a square minus a to the power 4 by r square into dA. Is this point clear? Now this is the only important point. So this becomes 4 pi rho naught a cube by 3 minus a5 by 5 r. Before there was r square. Right, and then you have to put the limit 0 to r. So you see q inside is equal to 4 pi rho naught. If I take r cube outside, 1 by 3 minus r square by 5 r square, right? Now this q inside is equal to, sorry, this q inside divided by epsilon naught is equal to whatever is the field radial, right, into 4 pi r square, right? Because this was integral dA, right? So my field will become 4 pi rho naught r square r rho naught r by epsilon naught 1 by 3 minus r square by 5 r square. Right? Is this clear to everyone? Now this is valid for r less than big R. Right? If you go for r greater than big R, then you can take this entire charge and put it on the origin, and then it will have the hyperbolic relation, right? As we know, for r greater than or equal to r, the field is whatever is q total by epsilon naught 4 pi r square, right? So you can see these are two functions, and your field will be complicated. Then accordingly your potential will be complicated by